calculus lesson, the derivative as a function. Alright guys, oh, I forgot to write down the objective here. So the objective is to understand derivative and do derivatives and what exactly is a derivative, right? And we're going to be learning about higher order derivatives and things like that. Okay, so continuing from the previous lesson, all we did over here, guys, is we switched the letter A to X. Hence, the derivative of the f is defined as the f prime of x, of limit as h goes to 0, f of x plus h minus f of x. Now, what is the implication here, guys? What is the implication of, rather than using the letter A, we're doing it in terms of x. See that right there? So that is in terms of x, not a. The difference is that a represents a specific number and a represents a variable that can change, right? It's a bit of a semantic, but it's an important one, okay? So when you have f prime of x over here, guys, right, is the general equation of the slope of the given function f of x. Okay, so if you apply this, right, whatever the result, that is the slope, equation of the slope for this function. Now, if you sort of think about it, right, we will talk about that in a second, but let's look at this over here, guys. That's change in x, a y value. This represents a change in x, right? And I just wanted to introduce you to a new notation. Now, the interesting is that that's what that is. But we are saying that the change in x will get smaller. So, when you have a limit as change in x goes to 0, it's x, the delta x becomes smaller and smaller and smaller and smaller, and the y becomes smaller. Oh, okay. So what that implies is that instead of having capital, you know, the triangle is a capital delta. The small delta has a small letter d. So we actually denote that with dy dx. This right here is called, like Leibniz's equation, a notation, and this is a prime notation. So this is often called f derivative f, right? Is the f prime. We'll talk more about that. Okay. So the other notations that we have is basically f prime of x, y prime of x. We got Leibniz's dy dx, d dx, because y could also be written as a f of x, right? Perhaps I should pull this down a bit. Okay, there you go. And then you could just go df dx, because sometimes we don't write f of x, we just write f, right? It's a function. And sometimes we may put big D of f of x, or we have big D differentiated with respect to x. There are lots and lots of notations, but the ones in the beginning are the ones that you're going to see the most often, right? So if it looks like a fraction, it's Leibniz. If it's has a little apostrophes, that's prime. That's a Newtonian notation. Well, this looks really harmless, doesn't it? So it's basically asking us, given this tangent, what is the slope at that point? So what we would have is something that looks like this. At pi over 4, what's my slope? That looks like more than 1. But as it turns out, I was being a little bit too... yeah. So there's something that you need to know in order to do this. And even then, it's going to be a bit much. and that thing that you have to know is that limit of h goes to 0, sine of h over h is equal to 1, right? So I want to know if you could show that this is true and why this is true. And I like to save this one for class because it's a bit of a doozy. So I want to be able to walk you through this. So let's try something else, right? That's a little more familiar. How about example 2 from your book, right? Let's try f of x is equal to x cubed minus x. How do I find f prime of that? Well, f prime of that is the limit as h goes to 0 of f of x plus h minus f of x over h. And let me move that down here so we'll have more space. Okay. So when you do all that, because what we have is x cubed minus x, anytime that's x, we're going to instead write x plus h, right? And then, oops, x plus h. Sorry. I should be more careful. X plus h. And then f of x is as it is. X cubed minus x, whole thing over h. All right. So let's do some expansion here, guys. All right. So this right here is x cubed 1331. Remember that? 3x squared h plus 3x h squared plus h cubed minus x minus h, whole thing minus x cubed minus h, everything over h. And we have cancel out the h cubed, cancel out the x, and you will notice that everything here contains h term. So when you factor out and divide that, we actually end up with a limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 1. And because this expression is polynomial and anything other than h, we consider that as a coefficient, right? It's polynomial. So we're going to plug in, we could do a direct substitution. And we end up with that goes to 0, that goes to 0. Therefore, the answer is 3x squared minus 1. Oh, wow. So when we did the derivative of the cubic, it became a quadratic. Nice. Okay. All right, so that one was fairly doable. Let me actually move this around a bit. Oopsie. All right, let me make that a little smaller, just to show that we're going to go over in class, right? But I'd like to do another one, right? Because that tangent will be fun tomorrow. All right, so let me choose a slightly different color. Example, I don't know, 3 from your book. So let's go f of x is root x. We're doing something a little bit more approachable. Let me zoom in a little bit, guys, okay? So f prime of x, I'm going to just go right directly, guys. Okay, h goes to 0. It's of f of x plus h, right? Minus f of x. So for f of x plus h, you just replace all the x with x plus h. Minus f of x, which is as it is, over h. Now, when you have that, what do we do? If we said multiply by the conjugate, you're absolutely, positively correct. Now, when you do that, it becomes x plus h minus x. Whole thing over h, square root of x plus h, plus root x. X is cancelled. You see that h is cancelled? Yes, it does. So we have the limit as h goes to 0 of 1 over square root of x plus h minus plus square root of x. looks like I could plug in h and nothing bad's going to happen, right? Then you could do that. So 1 over square root of x plus 0 plus square root of x. The whole thing becomes 1 over 2 square root of x. Yay. Yes, that's exactly how you do it. Well, let me give you a little bit of a hint as to what you can do for, just give me 1 second, let me rearrange these. All right, so what, now that I have some space, I could expand this out. There you go. So that's what I expect to see. And make sure you have a room to work this one out. This is going to take a bit of a space. Now, this is going to be a tangent of x plus h. You're going to be expanding that out. So you're going to have to know your, that's right, trig angle addition formula. Okay? And in the midst of doing this, notice that tangent could be expressed as tangent x over cosine of x. That's right. So you might want to get into that. And that's where this thing comes in. Okay? Now think about this. Can you tell me why this is true? It's true. But why? Key is to think about what is sine of h actually mean. All right? I'm trying to prime you for a discussion tomorrow. Okay? All right, guys. So let's move on to the next topic. There you go. Let's see. All right, guys. So we have some definitions of what is differentiable, right? So function f is differentiable at a, right here, guys, right? If f prime of a exists and it is differential on open interval ab, or any one of that, if it is differentiable at every number in the interval. As long as it is differentiable on every number in the interval, we say that the function is differentiable. Whoa, so what did we just say? IOW, ow. Well, you know the words, right? If function is differentiable at x equal to a, if one of two things happen. If, number one, function is continuous at x equal to a. Right? What that means, the reason why, now think about why that matters, okay? But what that means is that the limit of x goes towards f of a has equal to f of a. So this means that the left limit, the right limit, I realize I wrote that sort of backwards, right, is the same. When you don't have a sign right behind it, it means it's two-sided limit, right? All right. So we know that function has to be continuous. That's the first thing, right? And the second is that slope is continuous at every point A. What that means is that the left slope and the right slope has to be the same. In other words, this expression from the left and from the right has to be the same. Wow. Think about it. So if you have some point over here, x equal to a, so when you come this way, the slope over here and slope on the right, they have to match. That's what they're saying right there. Not only that, according to this, it has to be continuous, so you can't have a hole. Wow. Yep, that's what it is. Now, the question arises about this one. Where's the function f of x, absolute value of x, differentiable? More importantly, where is it not differentiable? And immediately when you draw the picture, you can tell right away, to the left of 0, it's a straight line. It's a form of polynomial. To the right is a straight line, so it's continuous. But what about here? Is that differentiable? The key word that I want you to sort of look at is that the slope from the left and the right has to be the same. But when you do that, it creates a, are you ready for this, guys? Smooth surface. Yeah, smooth. I said that. So when you see something that's differentiable, it's smooth. As opposed to what? We'll get there in a second. Okay. Now, let's think about this. Okay. We know that it meets this requirement. It is continuous at this point. You don't have to take off your pen or pencil to draw this graph. Then comes the second one. What was the left and the right slope? Obviously, my left slope is -1, right slope is +1. Therefore, over here, it's not differentiable. It's not smooth. It's sharp, isn't it? Okay. But we need to be a little bit more rigorous, right? So what is f prime of 0? That's basically what? Limit as x is going towards 0, f of x minus f of 0 over x minus 0. And when you do that, it's limit as x goes to 0. When you plug in the values, that becomes absolute value of x minus 0 over x minus 0. Is not limit as x goes to 0 of absolute value of x over x. Wait a minute. That's the signum function, right? What that means is that, f prime of 0 is 1 when x is greater than 0. It's -1 when x is less than 0. So, left and the right is not the same, right? So because of that, we could say that since f prime of x is dne, does not exist because left and the right is different, right? We could say that f of x is not differentiable at x equal to 0. That was it, guys. All right, so let's talk about the general shape. Jump we know, so there's a bit of a jump. Removable is you could have some sort of nice, let's go with partial. There you go. Hole right there, and that point has been removed, and it might have been put somewhere else or nowhere at all, right? And that in infinite asymptote, so this is different kinds of something that's not differentiable, right? First, none of these are continuous. If it's not continuous, it can't be differentiable, period. But even if it is continuous, there are cases where it is not, and that's when you have vertical tangents like this. If you have, let's say, a semicircle right here, the vertical tangents, or a corner, we just saw one, right? So something like a V shape, maybe something a little less pronounced, maybe it's even something like that. But there's something called a cusp. Cusp is actually, it's like this. It's hard to describe, but it creates a very sharp point. Well, that's not true. Like this V shape, it could be sharp. It could be like really sharp, right? But it sort of curves into it. It's almost like they're going to be a tangent to each other, right? That's called a cusp. Okay. If you're interested in that, Wolfram Alpha has some pictures and some arguments about it. Just click on that link if you download the PDF, and it'll take you there. Okay. All right. So in class, we could sort of watch that together. Okay. All right. So let's just practice some graphing this, and we'll do a couple, and then we'll do the rest in class, right? And I think that's only fair. I don't want to spend too much time online. Yeah. Why don't we just do a couple? And we could do the rest as an exercise, right? Let me do the easy ones. Okay. This one. Basically, what this says is that we have given... I think I did it backwards. Right? I meant to say, because that's actually much harder. Okay? given the function, I meant to say f prime of x. No, I did it again. Jeez. All right, let's go back to blue. That's what it is. Given the function, we want you to graph the slopes. Now, the ones in the bottom is the other way around. That's actually a little bit more difficult. Okay, well, we'll figure it out. Okay. So now we're asking you, right? Given that straight line, how do you draw its what do you call this thing? Slope, right? Well, the thing is that if you think, let me zoom that in a little bit, okay? If you just draw something like this, right? You can sort of estimate it. That's whatever that is, length. Oh, it looks like this. Looks like the height is twice that, right? Change in x, this change in y. If that's 1, that thing looks like it's a 2, right? So we could sort of, because it's a linear equation, the slope here is equal to 2 over 1, which is 2. That's our best estimate. Yeah? Yeah. And this one over here is a linear equation. You could see. And if it's a polynomial, it will have degree of 1. And my slope will be 2. You go 1, 2. There you go. Hey, wait a minute. What I just drew, isn't that a constant? Constant is just a number, right? So linear equation when you take the derivative became constant, and degree of polynomial on this one is 0 because it's just a number. How about this one over here? Let's do the zeros first. See that slope right there? See that slope? It's about here and here. My slope's a 0. So this is the f. This is the f prime. That is the f. That's f prime. And around here and here, maybe a little inside, my value, sorry about that, is 0 and a 0. Now, right in the middle though, right? See this right there? I want to choose the middle, right here. And my slope appears to be, I don't know, -3, okay? So right around here, my slope is 1, 2, yeah, it's about here. -3, okay? And then let's go maybe here. Oh, look at that slope. But most importantly, go about the same distance. They seem to have the same slope. It's not strange. And that's even steeper than this, maybe 4. So coming here, my slope is like maybe 4, maybe up here. If you try to picture that, right, it almost looks like it's going down and up, almost like a polynomial. Actually, it is, okay? So if you draw this picture over here, guys, this one is cubic equation, and the degree is what? 3. One below that, when you take the derivative, this appears to be the quadratic, and one below that is degree 2. Okay? All right. So I'm going to leave the rest for you guys to, oops, I can't show you the answer. For you guys to do, and after this page, we got one more to do. All right, guys? So we got enough to do in class. All right, guys, that'll be the end of the online asynchronous lesson. I'll see you in class, guys. Bye-bye.